Continuing section 5.2, which is about probability. Definition. Actually probability models, but probability models. Event. So what is an event? I think I kind of mentioned it in the last video a little bit, but formally an event is a collection of outcomes from some chance process. That is, an event is a subset of the sample space. Events are usually designated by capital letters like A, B, C, and so on. So S kind of denotes all the possible outcomes. And then we list these events A, B, C that are basically just subsets of this. You know, they might have all of them, they might have some of them, they might, I guess you could even have none of them, for example. But it's a subset. So the random phenomenon, random phenomenon, let's roll a die and record the face showing. So if I wanted to list a sample space, I could show a 1, I could show a 2, 3, 4, 5, 6. So those are the outcomes, those are the faces that could show up. So we could define event A to be you get an even number. So this would be in words. This would be the actual subset. So if you're looking for even numbers, you would just basically look at the even outcomes. So as you can see, this is a subset of that. Basic probability rules. All right, so this is where we're really starting to get into some actual probability. Probability of an event is a number between 0 and 1 inclusive. I think that's pretty self-explanatory. Or 0% and 100% if you want to think about it in terms of percentages. An event that has a probability of 0 will never occur. The event is impossible. And it's not unlikely to occur. It's impossible to occur. An event that has a probability of 1, then that event will occur. That's a guaranteed, absolutely guaranteed event to occur. If the probability of all outcomes of a random phenomenon added together, if the probability of all outcome of a random phenomenon added together must add up to, okay, so I guess what I apologize for is not that I can't read it, it's that I can't write it. Basically, if you look at the probability of all outcomes for a random event, those outcomes must add up to 1. Those outcomes must add up to 1. That's kind of a thing that we talked about when we were talking about probability models. Probability model has all possible outcomes and their associated probabilities. Well, if you have all the outcomes, then those must all add up to 1 because that is all of the outcomes. If it sums to a number less than 1, then there's some outcome that's not included that is a possibility. And if it's a possibility, then it should be an outcome that's in the sample space and in the probability model. If all outcomes of a random phenomenon are equally likely, then the probability of event A is. So most people think of this right here when they think about probability. That's kind of like a theoretical probability if you have equally likely outcomes. So the probability of event A, so this is the notation we use for probability of event A. It's the number of outcomes that are favorable to an A divided by the total number of outcomes. So that's kind of up here. If I wanted to calculate the probability that you get an even number, first we need to assume that we have a fair die, meaning all of these outcomes are equally likely. So if they're equally likely, then I can use this formula. So the probability of event A is all the outcomes favorable to A, so that would be 2, 3, 4. There are 3 of them. 3 is the number of outcomes favorable to A, divided by the total number of outcomes, which would be 6. If you roll a die, the probability you get a even is 1/2, as you know. The probability that event A does not occur is equal to 1 minus the probability that event A does occur. The probability that event A does not occur is called the complement of A. So yeah, this is a definition of the complement. The probability, what's the probability that it rains tomorrow? If the probability that rains tomorrow is 70%, then what's the probability it doesn't rain? Well, if there's a 70% chance it rains, then there's a 30% chance that it does. Or does or doesn't. You get my point. Those are complements. They're 180 or 180. They're 1 minus each other. That's it. We denote that A complement, and it is simply 1 minus the probability of event A. This is going to come into play for certain questions. The idea here is that sometimes the complement of an event is much easier to calculate than the event itself. Well, if you can calculate the complement, then if you just take 1 minus it, you can get the other probability. So it's going to be another tool that we add to our little probability tool belt. Example, car repairs. So I think we had this as an example before. So the probability that I have 0 repairs in a year is 40%, 1, 2, and then 3 or more we kind of group together. Let B equal a car requires less than 2 repairs in a year. So find the probability of event B. So if I wanted to look at the actual outcomes for event B, a car requires less than 2 repairs. So less than 2 repairs would be 0 or 1 repairs. So those would be the outcomes favorable to B. In this case, I can't use, these are not equally likely outcomes, so it's not like it's going to be 2 out of 4. The probability of event B is simply going to be these two probabilities added together. That's 0.4 plus 0.35. See, in I feel like my notes are maybe a little bit out of order. I think this is certainly something that we can understand, but I feel like we're talking about the addition rule, which I'm going to introduce down here. But this is all right. I mean, come on, it's those two added together. What's the probability of B complement? Well, if I know the probability of B, this is going to simply be 1 minus the probability of B, because they're complements. 1 minus 0.75, which is 0.25, which could have just added those two together, right? The other two outcomes. Interpret B complement in context. This is the probability a car requires. So what's the opposite or the complement of less than 2 repairs? Well, that would be a car requiring 2 or more repairs. And you could word this differently, but you could say more than 1 repair. Whatever. Easy. Example. A chance process randomly assigns the digits 0 to 9 with replacement to the ones and tens place of a 2-digit number. This creates a 2-digit number where all the outcomes are equally likely. Okay, well, I thought I was going to have to think about it until they gave me this. If this creates a 2-digit number where all outcomes are equally likely, then I guess I kind of have it. But I should mention that the 2-digit numbers are going to be 0, 0, 0, 1, on and on and on, all the way up to 99, right? So basically, each digit, the tens and ones place can be any number from 0 to 9 with replacement. So that creates 100 outcomes. 100 equally likely outcomes. Find the probability the number is divisible by 10. Well, the total number of outcomes is 100. So we're kind of using this formula for number favorable divided by the total number in the sample space. So this is the total number in the sample space. So how many are favorable to the number is divisible by 10? Well, I guess we should just list all the numbers that are divisible by 10. 10, 20, 30, 40, 50, 60, 70, 80, 90. Now I would list 100, but 100 is not a possible outcome. The other one we do have to be a little careful about is 0. Is 0 divisible by 10? I would say 0 is divisible by any number, right? The definition of divisibility is when you divide it by 10, you get an integer, I think. I don't know. So I'm going to say 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I would say that is 1 out of 10, or 1%, or 10%, or 10%. I don't care if you list fractions, decimals, or percentages. The only stipulation I would say is if you're going to use percentages, you have to give me a percent symbol. If you're going to use decimals, of course, you have to give me the decimal. And if you're going to give fractions, I do actually want the fractions simplified. You have your calculator, so you should be able to simplify any fraction, no matter how ugly, at the click of a button. All right, so the next idea is kind of a significant one, and this will be the last idea in this video. Mutually exclusive or disjoint events. Mutually exclusive events or disjoint events. And I think this is probably something you've heard about before. But if not, this is a topic you got to come to terms with in statistics. So two events are A and B are mutually exclusive or disjoint. So these are synonymous words here. If and only if they have no outcomes in common, so can never occur together. So basically, I guess the key to this is they have no outcomes in common, or they can never occur together. In other words, the probability that A and B occur together at the same time would be 0. So this is kind of the mathematical definition, and then this is kind of the conceptual definition. We're going to have to switch between these. Sometimes we're going to want to use the mathematical definition. Others, we might just want to think about it. Identify if the events A and B are mutually exclusive or not. Random phenomenon. Roll a die once and record the face value. So my sample space would be 1, 2, 3, 4, 5, 6. Event A is we get a 6, so event A is just that outcome. Event B, we get an even number, so that would be the outcomes 2, 4, and 6. So the question is, are these mutually exclusive? Well, they are not, because they share a common outcome of 6. So these are not mutually exclusive. Random phenomenon. Flip a coin and roll a die and record the coin toss and number shown. So the sample space would look like record the coin toss and the number shown. So it'd be like head 1 or tail 6 or head 3, on and on and on. Okay, that's what I'm recording. So event A is the coin is an H. So this outcome would have all the outcomes that are so it'd be H1, H2, H3, all the way up to H6. Event B, die shows a 6. So that would be all the outcomes that are favorable to a 6. So that would be a heads with a 6 or a tails with a 6. So the question is, can these occur together? Yes, they can. And you don't need to list the sample space and talk about it. You can just think about it. Can you get a heads and a 6 at the same time? Well, if you're flipping a coin and rolling a die, then yeah, those can happen at the same time. So these would be, so if they can happen at the same time, then they're not mutually exclusive. Okay. Random phenomenon. Flip a coin and roll a die and record the coin toss and number shown. So same sample space as the one up here. Okay. Now event A is die shows a 4. So that would be head 4, tail 4. Event B, die shows a 6. So that's head 6, tail 6. So these do not have any outcomes in common. And again, I don't know why I'm listing these. You don't need to list them. Can you get a 4 and a 6 at the same time? When you flip a coin and roll a die one time, can you get both a 4 and a 6 on the die? Of course not. So these are mutually exclusive because they can't happen together. Okay? Random phenomenon is observe the weather on a given day. Sample space. I don't even have any idea how I would list the sample space. I could say, I guess it's going to rain, it's snowing, it's sunny, it's hot, it's cold. I'm not sure what these even look like. So let's just look at these events. A is that it's raining. So A is all the outcomes where I'm describing the weather and raining is part of my description, I guess. And event B is the sun is shining. So the question here is, can it be raining and the sun is shining at the same time? And some people might say, no, you can't do that. If it's raining, the sun can't be shining. But I think you guys would say these can happen together. I think if we've all had those days where the clouds are kind of off to one side and the sun's shining from the other angle and we're getting rained on, but it's sun is shining. So if these can happen together, these are not mutually exclusive. Okay? More of a conceptual one.